Um, so, how did you go with the work from last week? Pretty good?
Yeah, pretty good.
Do you have any questions about it?
Not really, no.
Okay. Is it so I have created a Google Classroom for this as like kind of like the new step forward, I guess.
Yeah.
So, is it possible that I can give you the code to the Google Classroom and you can join?
Yeah.
All right, cool. I just put it in the chat.
Yep. Sorry, just give me a second.
No problem, take your time. So, yeah, it's essentially just going to be a Google Classroom, just like how it is in school, although we're not really like school. So at the moment, I have the chemistry introductory lesson, which was the admin stuff that we went over. I have included the module 1 booklet, although I may have to make some alterations to it, so I'll do that in the future. And I've also posted up 2 assignments. Your assignment is just essentially your weekly homework. You've already done the first one, so that was last week, so I didn't particularly really care or bother setting a due date for it since you've already done it. But the latest one, so homework 2, that will be your homework for this lesson.
All right.
So it's just a Google form and then I'll mark it and you'll get it back straight away.
Okay.
Do you have any questions about that?
No, that's fine.
All right, no problem. If you have any questions or concerns, you don't have to type it up on here. You can just message me straight away. I gave you my phone number, yeah?
Yeah.
All right, cool. Yeah, so there shouldn't be any issues. Okay. So just a question. Have you started chemistry at school or only with me?
I have started chemistry at school.
Yeah.
So, but the school's not allowed to start the new syllabus until the start of next year.
Mm-hmm.
So right now we're just doing revision from year 7 to 10.
No problem. Okay. Cool. Yeah, that's essentially all I asked because I have another student for you. He's in Year 10 as well, and he's doing physics, and he said that he already started, and I'm just like, I don't think that's allowed. So
Yeah, or it's not allowed.
yeah, so I was just kind of asking, just like, see if nothing's changed.
Yeah.
All right, cool. So today we are essentially just going to be continuing our work. So we left off last lesson with looking at the periodic table and all of the different properties of different elements assigned in their relative groups.
Yep.
Okay, so today we're just going to be starting from page 17. Page 17 listed, but page 19 in the actual document. So just the naming compounds.
Okay. Yeah, I'm on it.
All right, cool. So I presume that you have some background in naming compounds, so I hope that this can be pretty insightful.
Yeah.
So firstly, I have to go over some things. So do you know what an element is? And basically all the terms on the page, do you know what they are?
Yeah.
Okay, can you tell me what all of them are?
An element is basically a pure substance found naturally.
Mm-hmm.
And a molecule is a combination of 2 or more elements.
Yep. Or actually, not necessarily 2 or more elements, because O2, oxygen gas, is considered a molecule.
Oh,
Of to say 2 or more atoms.
atoms. Yeah, that's a better word. And then a compound is 2 or more elements.
Mm-hmm.
An ion is when a particle of an element loses or gains more electrons in its valence shell.
Perfect.
So gains a positive or negative charge.
Yeah, that's 100% correct. Good job. So that's essentially the groundwork, but we're going to be kind of looking at different types of ions in particular. So it's very important to establish what ions are. So if we go to the next page, we have some definitions. So we have organic compounds and inorganic compounds. Now these are important because they are the focus of some future topics. So organic compounds are essentially compounds that have carbon. So in a nutshell, if it has carbon, it's organic.
All right.
And then conversely, anything that is inorganic, it's not going to have carbon.
Okay.
Yeah. But so if we further break that down, we can actually get different types of compounds. So don't worry about organic compounds. That's a year 12 topic, so you'll be all good for that by the time we get there. But we're going to focus specifically on inorganic compounds. So things that don't really contain carbon. So as you can see, there's two different types of compounds, inorganic compounds. And it's all dependent on the way that they're bonded. And we're going to find that out later in this module. So firstly, we have ionic compounds, which are compounds that are made up of ions, such as sodium plus and chlorine minus. And as you can imagine, because one is positively charged and the other is negatively charged, not necessarily, just this example in particular, they're going to have a strong electrostatic attraction that results in a compound being formed.
Okay.
Okay, and then the other one, which I hope you've heard of, is covalent compounds. And covalent compounds are made up of generally two or more non-metal atoms. So what's the difference between ionic compounds and covalent compounds? Well, covalent compounds actually do not have ions in them. So that means that nothing has a strictly positive charge and nothing, has a strictly negative charge. So that means that the strength of these compounds is going to be weaker than ionic bonds. And this is because the electrons are shared rather than taken away, like ions when something gains or loses an electron.
Okay.
Does that make sense?
Yeah.
Okay, cool. So next on the agenda is ions. So we've already defined that ions are elements that gain or lose electrons. But there's general rules that we can actually see regarding ions. So the first general rule is that group 1 metals have a +1 charge, group 2 metals have a +2, group 16 have a charge of -2, group 17 have a charge of -1, and the transition metals are up in the air. So I'd just like to demonstrate this on my periodic tables for a second. So I will, perfect. So on my periodic table, we can see what's happening. Well, the idea is that the charge is going to correspond to the group. So this is going to be +1, this is going to be +2. All of these they have their own rules. Generally, they're +2, but they'll let you know otherwise if they're a different one. So for example, if I had iron, so Fe, you would assume 2+. But however, if I had iron, bracket 3 in Roman numerals, that would mean iron 3+.
Okay.
Yeah.
Yeah.
So if we continue, so this would be typically +3, this is typically +4, and then we have -3, -2, -1, 0.
All right.
Does that make sense?
Yeah.
All right, cool. So it's just a logical progression because essentially the ionic charge is equal to how many electrons it has in its outer shell.
Yeah. Okay.
Yeah, but do you understand why these are negative?
They gain electrons rather than losing them, unlike the first few groups.
Yeah, that's essentially it.
Yeah.
Cool. So next is polyatomic ions. So you may be familiar with the fact that sodium is an ion or chlorine is an ion, so on and so forth. But there are ions that can actually have more than one atom, and these are known as polyatomic ions. So it says here that these ions have their own names and formulas which must be remembered. So you actually can't figure out the name of the polyatomic ion when we get to it using the rules. You just actually need to understand them.
Okay.
So ammonia, NH4 plus, ammonia, NH3, hydroxide, OH minus, nitrate, NO3 minus, sulfate, SO42 minus, phosphate, PO43 minus, and carbonate, CO32 minus. There's actually others that I can give you if you want, but these are the most common that you will experience.
Okay.
Any questions?
No.
All right, cool. So if we go to the next page, we can finally get to what this dot point is actually about. And it's about naming ionic compounds. So the idea for naming ionic compounds is that, well, ionic compounds are generally made up of a cation and an anion. Do we know what cations and anions are?
Cation is negative charge, and anion is a positive charge.
Okay, it's the other way around.
Oh, other way around. All right.
Yeah. There's two really cringy ways to memorize it.
Okay.
So the one that my teacher told me is cations are positive because it's like a pun on positive.
Oh.
Yeah. And then the other one was anion, which sounds like onion, which makes you cry. So it's negative.
Oh. Okay, I get it. Yeah.
Okay, yeah, it's pretty cringy, but it works. So yeah, I don't refrain from using it.
Yeah.
Okay, so yeah, so the idea is we name the cation, so the metal first, and then we have the anion, non-metal second. So cations are positive ions, anions are negative ions. So the next step is going to be that we're going to add the appropriate suffix to the anion. And typically this is "ite". And we have examples here. So NaCl is sodium chloride, following those two rules. AlO2 is ammonium oxide, etc.
Okay.
However, one thing that we must note is that you may have thought, hang on, for AlO2, that is two oxygens. So shouldn't it be dioxide, like carbon dioxide? And the answer to that is it doesn't apply for ionic compounds.
All right.
Yeah. So as the thing says below it, basically when naming ionic compounds, the cation retains the same name as the element. The anion's name is similar to the elemental name, but the ending of the name has been removed and replaced with "ite".
All right.
Okay. So for covalent compounds, we're going to learn about electronegativity very quickly, but we're going to come back to it later on. So the idea of electronegativity is, as the definition below, is essentially, I'm going to have to read because these are my own words, the measure of the ability of an atom to attract electrons for chemical bonding. So essentially, it's the attractiveness of electrons.
All right.
So if we were to go back to my periodic table earlier, so this is concerning the number of ions, the ionic charges, so I'll keep that up. But if we go to this little diagram, what elements are going to be more likely to gain what color? To gain to gain electrons? Hydrogen or fluorine?
Fluorine.
Why fluorine?
because it has to gain electrons in order to have a full valence shell.
Yeah, that's essentially it. You put it very well. So because fluorine has more elements in its outer shell than hydrogen, fluorine is more likely to get 1 electron to complete its outer shell than hydrogen is to get 7 electrons to complete its outer shell, isn't it?
Yeah.
So that's essentially what electronegativity is. And the idea of electronegativity is that it increases this way. So the elements in the top right corner of the periodic table are much more likely to attract electrons than elements on the lower left side of the periodic table.
Oh, okay.
Yeah. And I can just quickly explain why electronegativity decreases down here. Electronegativity decreases because each period I gain a new orbital shell. I have a new valence shell.
Yeah.
Okay, so if I gain a new valence shell, that means I already have so many electrons, don't I?
Yeah.
So how likely is it for me to gain another 7 electrons for potassium compared to hydrogen?
It's not very likely.
Yeah, and that's because potassium is going to have what, 4? So we have K, oh, it doesn't like me drawing on there. So we have K, 1, 2, 3, and then 1 electron here, 4. So because all of these shells are already filled, and I apologize for the really bad drawing.
That's okay.
The idea is that because all those shells are already filled, the more shells you have, the less likely it is for a reaction to occur.
Oh, okay.
Well, not as, that's probably a bad way of putting it. The less likely it is to complete its outer shell and for a reaction to occur.
Okay.
But a reaction still can occur, but it's more likely to lose the electron rather than gain it.
Yeah. Okay.
So, in your own words, what is electronegativity?
It's basically how likely an element is to gain electrons.
Yeah. And what are the general trends? So this is important because we have to figure out which element we put first.
So from the bottom left of the periodic table to the top right, the electronegativity increases to the top right.
Perfect. So that means that fluorine is the most electronegative compared to what was like sodium, which isn't very electronegative.
Yeah.
Okay. So now back to actually naming the compound. So we're going to name the element with the lowest electronegativity first. So we're going to name the element that's more to the left. Then we're going to add the appropriate suffix to the second element. This is typically "-ide". And then we're going to add a prefix to both the first and second element to indicate the number of atoms. So the prefixes are mono, di, tri, tetra, penta, hexa,
Yeah.
etc., etc. But the only rule that is a little bit different is that we actually don't add mono to the first element. So we can see in the example I have carbon dioxide, but technically that should be mono carbon dioxide. But due to the conventions around naming compounds, we just leave it as carbon dioxide.
Okay.
But this is contrasted with dichlorine monoxide, where if the secondary element has, if the secondary element is only 1, then we apply the mono prefix.
Yeah.
Okay. Another rule is that when polyatomic ions create covalent compounds, The polyatomic ion will never have a prefix.
All right.
Yeah. So there's an example there, AlNO3, 3, which is ammonium nitrate, but by our conventions, it should be aluminium trinitrate. But because nitrate is a polyatomic ion, we don't bother with the prefix.
Okay. All right.
Yeah. There's also further naming rules, and these are by a board that's known as IUPAC, which is essentially like the chemistry board of the world, I guess. And their rules are essentially, so this is kind of straight from the textbook, so I'll just kind of read it. Single atom ions are named with an "ide" suffix. So, for example, O2 minus is going to be oxide. Cations with more than one possible charge must have the charge indicated after it in Roman numerals. So this harkens back to what I was talking about earlier. So remember how I said ion is typically 2+, but you will know if it's going to be 3+ if they have the 3 in Roman numerals next to it.
Yeah.
Cool. And then the last one is very important relating to polyatomic ions. So oxyanions are named with "ite" if they have less quantity of oxygen. So that kind of doesn't really mean anything unless we provide an example. So the example I gave is NO3 minus is nitrate, but NO2 minus is nitrite.
All right.
Yeah, and so if PO4 3 minus is phosphate, what will be PO3 3 minus?
Okay.
What do you think it would be?
Sorry, can you ask the question again?
No problem. If PO4 3 minus is phosphate, what will be PO3 3 minus?
Phosphite?
Exactly.
Yeah.
Yeah.
Okay.
And what would SO4 2 minus be? So like, do you remember like you might just go back and check it anyway, so I may as well say it. SO4 2 minus, what would SO3 2 minus be?
Sulfite?
Yeah, you get the idea.
Yeah.
Okay. And the good part about having all these rules, so all on these pages, all these rules, is that you can use them both to name something, but to also come up with the chemical formula for a compound or an element or whatever.
Okay.
But unfortunately, because it doesn't really work with polyatomic ions, you must absolutely know all of your polyatomic ions.
Oh.
Yeah. And they're not going to be like, what I mean by that is that they're not going to ask, like when you see your preliminary, for example, they're not going to ask you, NH4 plus is what polyatomic ion is, just worth 1 mark. They're not going to ask you that. They're going to give you a chemical equation, and in that chemical equation is going to be the polyatomic ion. So you're expected to know the polyatomic ion, so then you can solve the rest of the question that isn't necessarily related to it.
All right. Okay.
Yeah, so it's pretty important.
All right.
Okay, there's a concept check on the next page. Can you please complete it?
Yeah.
Yeah, thank you.
So do I just say it to you? Is that okay?
Oh no, can you actually write down, please?
Yeah. Yeah. Okay.
Oh, and please tell me when you finished.
Okay.
Yeah. Just make that clear.
I'm done.
All right, cool. So let's go over your answers.
For the first question, compare and contrast the properties of metals, non-metals, and metalloids. Metals are lustrous, they're good conductors, they're malleable and ductile, whereas non-metals are insulators, which are the opposite of conductors. They're brittle and they are gases at room temperatures, unlike the solid metals. And metalloids have both non-metal and metal properties, and some of them can conduct electricity or heat in certain circumstances.
All right, cool. Just one thing. Non-metals, not all non-metals are gaseous. So generally they are.
Okay. Okay. Question 2. Cations have a positive charge. Anions have a negative charge.
Mhm.
And polyatomic ions have more than one atom.
There's something a little bit extra about polyatomic ions.
Well, there's several ions together.
Okay. Can polyatomic ions be both positively and negatively charged?
No.
Really?
Well, the ions within them can, but
Okay, let's go back 2 pages to where it said polyatomic ions. So we can see on this page that ammonia has a charge of +1, the hydroxide has a charge of -1. So polyatomic ions can be both positively and negatively charged, can they?
yeah,
But what's the difference between a polyatomic ion and a cation?
they're not always positive.
No, no. In terms of like their structure, like what are they made out of?
One or more, like more than one
Yeah.
atom.
Yeah, so polyatomic is in its name, poly, which means more than one, whereas cation and anions refer to just a singular element has either gained electrons or received electrons. Wait, the same thing. Gained electrons or lost electrons. Whereas polyatomic ions can be both positively and negatively charged, but the distinction is polyatomic ions have more than one atom.
Okay, all right, I got it now. Question 3A is sodium carbonate.
Yep.
B, sodium hydroxide.
Yep.
C, I wasn't sure of the BE. Is it beryllium?
Yeah.
Yeah, so beryllium sulfate.
Yep.
And then D is hydrogen chloride.
Yep. Good. So essentially, you're going to have to remember the rules so you can name these without help being a couple of pages away.
Yeah.
Yeah.
Okay.
And what about question 4?
Question 4, ammonium sulfate.
Mm-hmm.
B, ammonium sulfide.
No. You were asked to write the equations.
Oh,
Does it say that? Or do you have a different version to me?
chemical equations.
Yeah.
Oh, yep. Okay, sorry. I wrote it
No,
in my book, so
all good.
yeah. A is NH3SO4.
No.
Um, NH4, NH4,
Okay, so what's your answer now?
NH4SO3.
Yeah.
And then B is NH4SO4.
Oh, actually,
Yeah,
um, we'll go back to question 4. So I'll kind of walk you through question 4 and you can use the idea for the rest of them. So I'll just quickly share my screen. Okay. So for question 4, we're asked to find, is this going to work for me? I don't know why. Okay, maybe I'll use my Word document. All right, so in question 4, we're asked to find ammonium sulfate. So I have the polyatomic ions here. So you proposed that ammonium sulfate was NH4 SO4. Yeah?
yeah,
So I just want to group them in brackets just to kind of show something. So if we have ammonium, normally it's NH4 plus, isn't it?
yeah,
But if we have sulfates normally, it is SO4 2 minus.
yeah.
So if I put ammonium and sulfate together, what will be my net charge?
Uh, -1.
Yeah. So the whole thing's going to be -1, but we don't want things to be negative when we add them together. We want them to be 0.
All right.
So do you know what you're going to have to do?
No.
Okay. So what you have to do, you have to make sure the charges add to 0. So the first one is going to be NH4 2 SO4.
Oh, okay.
Because the charges have to add to 0.
Yeah. All right.
Any questions?
No.
All right, cool.
So then B would be hang on. Um is sulfide a positive charge?
Sulfide.
Yeah.
Sulfide, why isn't this working? Sulfide is a negative charge, but you have to work out what it represents.
All right. So then it would just be NH4SO3.
What about bouncing charges?
Ammonium has a +1 charge. Sulfide has, is it -1?
-2. It's going to stay the same as its original counterpart.
Oh, okay. So then it would be NH4 2 and then SO3.
Yep.
Dihydrogen oxide. I got H2O2.
Okay. So you got the first part right, H2. But what made you think that there was 2 oxygens?
Uh, I don't know. It just came to me.
Okay, so is this an ionic equation or a covalent? Or is this an ionic compound or a covalent compound?
Covalent.
Okay, so if we go to the rules of covalent compounds, I'll just kind of read them. The very important one that we're looking for is add a prefix to both the first and second element to indicate the number of atoms. So for example, mono, di, tri, etc. Do not add mono to the first prefix. Do not add mono to the first element. Now, we can see here that we have dihydrogen oxide. Technically, it should be dihydrogen monoxide, but however, this is never really called that. So this is more of a trick question.
Oh, okay. So is it just H2O?
Yeah, it's just water.
Okay. All right. Then D, I got NaCl.
Yep, and that's it.
Yeah.
Do you have any questions about that?
No.
All right, no problem. So if we go to the next page, we're going to be starting 2 new dot points. So we're going to be investigating what an atom is. We're going to be looking at isotopes, and from that, we might get to radiation.
Okay.
So to begin with, what do you know about the atom?
I know its structure.
Mm-hmm.
I know I know the characteristics of like the parts of the atom
Mm-hmm.
and its electron configurations.
Good.
Yeah, that's it.
All right, no problem. All right, cool. So I'll just kind of skim through this a little bit. So we know that, well, in Year 11 chemistry and Year 12 chemistry, the atom is the smallest particle of a chemical element that can exist. So if you look at the structure of an atom, we can see, oh, actually, let me ask you a question. So we know that atoms are made out of protons, neutrons, electrons.
Yeah.
But why is it that the atom is the smallest particle of an element?
It, mm, Wait, I don't understand.
Okay, so we know that there are small particles than atoms.
Yeah.
Okay. But the definition of an atom is the smallest particle in an element. Can you tell me why?
Mm, no.
Okay. What is the definition of an element?
Sorry, can you repeat that?
What is the definition of an element?
Basically, a substance that can be found, a pure substance that can be found anywhere.
Yeah, that occurs naturally in nature. So why do you think an atom is the smallest part of an element?
Because the atom makes up the element?
Yeah.
Oh.
So an element is made up of a single type of atom. Hence, an atom is the smallest part of an element.
Okay.
Does that make sense?
Yeah.
Yeah, it's just definitions. And then from there, we can just kind of, it's made out of a nucleus, as we know, that contains the protons and neutrons. But however, one thing that you must know about the nucleus is that it contains the bulk of the mass of the atom.
Okay.
This is compared to electrons. So actually, the nucleus contains the vast majority of the mass, but almost none of the volume. The electrons contribute almost nothing to the mass, but contribute significantly to the volume.
Okay.
So, yeah, so we know that the electrons orbit the atom, but did you know that the electrons orbit the atom in an electron cloud?
Like the electron shells?
Yes.
Yeah.
Well, technically the electron shells actually isn't an accurate representation because there's many more accurate models of the atom. But yeah, for now we'll go with shells.
Okay.
Yeah. So this electron cloud, put that in quotation marks for now if you want to. It constitutes the bulk of the volume, but only very slightly to the mass, as I said. So one of the key things about atoms, and this is probably pretty trivial, but you may not have thought about it. A neutral atom is always going to have the same number of protons and electrons. Otherwise, it will become an ion.
Okay.
And that's very important because, well, the definition of an ion is when something gains or receives electrons. So that means that we can actually find the ratio of protons to electrons to find out the charge of an atom.
Okay.
Yeah. So the definition of a proton is a small positive, well, for chemistry, a small positively charged particle having the mass approximately equal to the mass of a hydrogen atom. Why is a proton approximately equal to the mass of a hydrogen atom?
Well, a hydrogen atom has only one proton.
What about neutrons?
Neutrons, they
Does a
they're
hydrogen atom have neutrons?
yeah,
Does it?
I think.
It doesn't.
Okay.
Yeah, the definition of a hydrogen atom is the most simplest atom for the reason that it essentially just has one proton and one electron.
Oh, okay.
Yeah, so that's very important to know because you're going to be asked to draw that and you can relate a lot of your responses to that. Yeah, and it has a charge equal in magnitude but opposite in sign to that of an electron because obviously they have to be equal and opposite. An electron is an extremely small negatively charged particle with the mass of approximately 1/2000th of the mass of a hydrogen atom. So that's why electrons contribute almost nothing towards the atomic mass because protons and neutrons are generally about the same mass, and then electrons are 1/2000th of that.
Yeah, okay.
Yeah. So do you want to know the mass of an electron and the mass of a proton? It's not necessary, but I can just illustrate my point.
Yeah.
Okay. So the mass of a proton, and I'm forced to remember this because I use it every day. It is 1.67 times 10 to the minus 27 kilograms. And I'll just share my screen because I wrote that without actually realizing you weren't looking. So that's the mass of a proton. The mass of an electron, so ME, is 9.109 times 10 to the minus 31 kilograms. So it's super small.
Yeah.
But, well, hang on. If these are the masses of the proton, because the electron is really small, if this is the mass of the proton, why on the periodic table do we have mass numbers in terms of 1, 2, 16, so on and so forth? Why do you think?
Uh, I guess to make it a little bit simpler, is that the reason?
Not really.
Make it more accurate, simplified?
Well, the simplification is correct. So I'll point you in the right direction. The idea is that we want a standard scale to make things easy. So, for example, hydrogen only has one proton and it has one electron. So on the periodic table, the mass is going to be 1.008 because that's the mass of a proton, standardized. So a proton is about 1, a neutron is about 1, and a proton is super small.
Yeah.
So we use it to create a standard scale.
All right. Okay. So
Yeah.
it's like a simplification, kind of.
It's a relative scale among the different particles because well, as you saw, 10 to the minus 27 and 10 to the minus 31, they mean absolutely nothing to us.
Yeah.
So because they mean nothing to us, when we do calculations and stuff like that, it doesn't mean anything. So like, for example, you're going to find out next module, which will probably be next year, in all honesty, that you'll be dealing with quantities that have 6.022 times 10 to the 23 atoms in them. Which is crazy. Once again, that number doesn't mean anything to us, does it? Because it's just so ridiculously big.
Yeah.
So the idea is that we create these standard scales so that things become simplified and we know what we're talking about.
All right. Okay.
Yeah.
Yeah.
So just to surmise, the mass of a hydrogen atom is 1.008. That is the mass of one proton and one electron.
Yeah. Okay.
Okay. And then, yeah, just to continue, a neutron is a small neutral particle, and a neutron has the same mass as a proton. Also, let me ask you another question. What do you think the purpose of the neutrons are?
I'm not exactly sure, but is it to do with the fact that a positive and a positive repel?
Yeah.
Yeah.
Yeah. So we're going to go over that on the next page, but that's a very good, I assume you hazarded a guess, and that was very good.
Oh, thank you.
Yeah. So essentially it is. So because the nucleus is so small, there is a small, not a small concentration, there is a large concentration of positive charges very close to each other. So as you said, like charges repel, but the idea of the nucleus is to kind of hold, the idea of the neutron is to hold the nucleus together.
Yeah. Okay.
Yeah. Do you have any questions about anything? I know the structure of the atom was pretty straightforward, but there were some new things.
Yeah. No, I'm fine.
All right, cool. So if we move on below the drawing, we're going to be looking at notation of atoms and certain things. So I just want to introduce this. This is right below the picture. So the atomic number, which is denoted as Z in notation, of an element is going to be the number of protons in the nucleus of an atom. And then very similarly, the atomic number is also going to equal the number of electrons in an atom, because protons and neutrons have to be equal to each other. And then secondly, the mass number. So this is actually on your periodic table. So like, hydrogen's number 1, oxygen's number 8, so on and so forth. That is your atomic number.
Yeah. Okay.
And then very similarly, the mass number is also on your periodic table. So hydrogen is 1.008, oxygen is 16.00. So obviously the mass number is going to be the mass you get when you add the protons and neutrons and electrons.
Yeah.
Mhm.
Alright.
The mass number is also sometimes called the nucleon number, and that is because, well, because the electron is so small compared to the proton and the neutron, you can often just neglect the contributions that electron make to the mass. So nucleon comes from the word nucleus. So it just means the number of the mass of the nucleus.
All right.
Do you have any questions?
Was it the mass number minus the atomic number, which equals the number of electrons?
No, the atomic number is the number of electrons.
Okay, okay.
Because the number of protons and number of electrons have to be equal. Otherwise, we have an ion.
Yeah. Oh, okay. Okay, now I get it.
Yeah.
And so then the mass minus the atomic number is the number of neutrons?
Yes.
Right.
Yeah, and that's how you get all of them.
Yeah.
Okay. Yeah, so you okay to move on?
Yeah.
All right. So on the next page, so now that we kind of got the idea of the general structure of an atom out of the way, we can actually talk about something called isotopes. Now, isotopes are very different to ions because with ions, we have defined them where a element either gains or receives electrons, and then because it has either gained or received an electron, there is an imbalance between the protons and electrons.
Okay.
Okay, so if we add or remove electrons, we create an ion. If we add or remove protons, what do you think happens?
Would it I'm not sure.
Okay, so remember that the number of protons is equal to the mass number.
Yes.
So if the number of protons were to change, would the atomic number change?
Yes.
So then what happens to the element? Say it's helium. What happens to it?
Does it become unstable?
No.
Yeah, I'm not sure.
Okay, no problem. I'll show you through a drawing. So hydrogen, actually, no, I was talking about helium. Helium has charge 4, and it has an atomic number of 2. So that tells me that it's going to have 2 electrons, and then 2 protons, and then 2 neutrals. Actually, I probably should use different colors too. Okay, so we have 2 electrons, 2 neutrons, and 2 protons. All right. Now, if I were to remove, so this is, I'm just going to write Z equals 2. If I were to remove a proton, that means that Z will become 1. So what actually happens is that this would actually change element and it would become an ion of hydrogen.
Oh, okay.
But however, this isn't necessarily true. There's another issue I would like to point out. So remember what I said about hydrogen. What is in the nucleus of hydrogen?
A proton.
Yeah, but we have 2 neutrons.
Yeah.
So does that mean that we're wrong? It can't be hydrogen, or is there something else we have to learn about?
the isotopes.
Yeah. So I don't know if you read ahead or if you actually knew that, but yeah, that's what we're going to be looking at.
Yeah.
So the idea of the isotope is essentially it's an element and it has a different number of neutrons. So for example, the example I love coming to is that helium is 2 neutrons, 2 protons, 2 electrons. Very nice, very straightforward. But if helium had 1 neutron or 3 neutrons, it becomes an isotope. So the golden rule about isotopes is that they are the same element. So that means that they have the same protons and they have the same electrons. The only thing that changes is the number of neutrons. So because the only thing to change is the number of neutrons, what do you think changes?
The mass.
Yeah, because all of a sudden we're losing a whole integer in our mass.
Yeah.
All right, cool. But the question is, okay, we know what they are, but how do we name them? Well, there's 2 different ways to name them, and you can probably see them in the image. So the first one is essentially just naming the chemical symbol with the mass number. So, for example, carbon 14, because that is an isotope of carbon that has 2 extra neutrons. Helium 3, which is an isotope of helium that only has 1 neutron, and then so on and so forth.
Could you explain that again?
Okay, so there are 2 ways to write isotopes, which are shown in the image on page 25 out of 83. And the idea for the first one is it's meant to be just very straightforward, very easy, just trying to state what it is. So what we do, we essentially state the chemical name, or the element name, or the element symbol, whatever you prefer, and then we have a dash, and then the mass number, which is just A, which is why I introduced the notation on the previous page.
Yeah. Okay.
So, for example, helium has a mass of 4, but if I take away a neutron, it becomes helium 3.
Okay.
Does that make sense?
Where did the 4 come from?
4 is the mass number of helium.
4 is the mass. Oh, okay.
Yeah. So with carbon, the mass number of carbon is 12. So if I were to add 2 neutrons to a carbon atom, it becomes carbon 14.
Oh, okay. Right.
Okay. The other way to write it is through the mass number, atomic number. I don't actually know what these are called, but as you can see, we have the chemical symbol, and then we have a superscript of the mass number and a subscript of the atomic number.
Yeah.
So it has the examples there. So 3,2H3 is helium 3 because the mass number is 3 and the atomic number is 2.
Yeah.
And then very similarly, carbon 14, mass number is 14, number is 6.
All right.
Does that make sense?
Yeah.
All right, cool. So the question that they can ask you about these that you'd actually have to do some maths on is relative abundance. So technically there can be an infinite number of isotopes of an element because it just depends on how many neutrons are in there. So like for helium, for example, I could have helium 3, helium 2, helium 5, helium 6, 7, 8, and so on and so forth.
Yeah.
But obviously, some isotopes are going to be much more common than other isotopes. Like helium 3 which is 1 neutron away from normal helium, is going to be much more common than, say, helium-10.
Yeah.
So the term that we use to explain these things is called relative abundance. So the relative abundance of an isotope is the percentage of that isotope existing naturally. So, for example, the copper-65 isotope has a relative abundance of 69.1%. So that means that if I were just to dig up a random sample of copper, 69.1% of it is going to theoretically be that isotope.
Ah, okay.
Yeah, and this is called the isotopic composition of an element.
Right. All right.
Does that make sense?
Yeah.
So although you may have been led to believe in year 7 to 10 chemistry that elements are generally pure and generally unshakable, isotopes are actually very, very common.
All right.
Sometimes isotopes can actually be more common than the element itself.
Oh, okay.
Yeah. So so you may for the copper example, you may think, oh, okay, copper wire, that is pure copper, but it's actually not. 69.1% of that copper is actually going to be an isotope.
Oh, okay.
Mm. Do you have any questions?
Nope.
Okay. So earlier you mentioned that the reason why we have neutrons in the nucleus is because it would be unstable.
Yeah.
And that's actually part of the reason. So this is a little bit of physics, but it's not actually physics. It's just kind of explaining some things. So in the nucleus of atoms, there are 2 forces. The first one is, as you correctly said, is going to be the repelling force on 2 positive charges. And that is known as electrostatic repulsion. The other force is very similar to gravity, but it isn't gravity. So because these particles are so small, it is kind of their version of gravity. So we just call it mass attractions.
Okay.
Yeah. So you can think of it as gravity, but it's not gravity.
Okay.
Do you get that?
Yeah, yeah.
Okay. So you never actually call it gravity. You just say the mass attractions. So so the balance between these forces keeps the nuclei intact because, well, think about it. The electrostatic repulsion is trying to rip apart the nucleus, but the mass attractions is keeping it together. So as long as the mass attractions are greater than the electrostatic repulsion, the nucleus is going to remain intact.
Yeah, okay.
And as soon as the electrostatic repulsion is greater than the mass attractions, you don't have a nucleus anymore.
Yeah, okay.
Okay, so theoretically, I'm still sharing my screen, damn it. Theoretically, that kind of makes sense. So if I were to add more neutrons, well, they're neutral, so they don't do anything electrostatically, but they will keep holding the nucleus together because I can load up on these mass interactions. But that's actually not true. So in larger nuclei, so these are elements that have an atomic number of greater than 82, and 82 is significant, and that is because, I'll give you a hint, the element that is number 82 on the periodic table is uranium. So you can probably piece it together from there. So right. Everything beyond that is radioactive.
Yeah, okay. Yeah.
Yeah. So after 82, there are too many particles, there are too many protons rather in the nucleus for the mass attractive forces to actually cancel them out.
Right, okay.
Yeah, so this means that we've reached that point where the electrostatic repulsion is greater than the mass attractions. So because of that, the nucleus becomes unstable.
Yeah. Okay.
And we call stable isotopes, so stable nuclei, it just means that they have enough binding energy. So it's the energy required to keep the nucleus together.
Okay.
So for stable isotopes, they have enough binding energy, but for unstable isotopes, they won't have enough binding energy to hold the nucleus together. So what happens, you may ask? Well, because they can't keep the nucleus together, you may think, okay, what's going to happen to the atom? Well, the atom doesn't implode or anything crazy like that. All it does is that it just gets rid of some particles. So for unstable isotopes to become stable, they undergo radioactive decay. So they release radiation. And because they release radiation, they are known as radioisotopes.
Okay.
Yeah, so this is kind of the segue into the radiation part of this module.
Yeah. All right.
Yeah, so the definition of radioisotopes are isotopes that spontaneously, so spontaneously just means that it just happens like, it's just like, all right, I'm going to do this now.
Yeah.
Yeah, they spontaneously emit radiation. So the radiation emitted is energy, and that energy is on the electromagnetic scale.
Yeah.
Do you recall the electromagnetic scale? So we have like radio waves, microwaves,
Yeah.
infrared, visible. Yeah, it's going to be on that scale.
All right.
Yeah. So you don't actually need to know what they are. Well, actually, no, sorry. You don't need to know the math behind them or anything like that. You just need to know what they are.
Okay.
Yeah. Okay. So now that we know what a radioisotope is, we can actually kind of, well, the syllabus requires that we actually learn about a couple because you can actually be asked to do extended responses on them. So this is from my old notes. So many radioisotopes occur naturally, such that of uranium, carbon, and hydrogen. So uranium occurs naturally, but it's pretty radioactive, isn't it?
Yeah.
Carbon can technically be Okay, the idea is that technically anything can be radioactive if the electrostatic repulsion is greater than the mass attractions.
Right. Yeah.
So carbon can technically be radioactive. So like say I have carbon 20, that's too heavy. So that can technically be radioactive. And the same with hydrogen. Hydrogen can also be radioactive if you add too many things.
Yeah.
Because if you add too many things, it wants to get back down to what it originally was.
Yeah.
Okay. So although there are naturally occurring radioisotopes, we've also made a couple, and they are the byproducts of nuclear reactors. So what happens is when we place an element in a nuclear reactor and we bombard them with other particles and then see what happens.
Oh, okay.
Yeah. So are you aware that we've made several elements?
Yeah.
Yeah, so when you look on your periodic table, when you go to the bottom right, you see those elements that have just made up names, like Einsteinium and things like that.
Yeah.
You're like, these aren't actually real things, but they actually are. They're real elements that have actually been made in labs.
Yeah.
But they're just so radioactive that it's absolutely crazy to actually have them around.
Right. Okay.
Yeah. So examples of radioisotopes that are used in industry include cobalt-60, which is used for the eradication of cancers. So it's like used in radiology, and it is made by placing cobalt-59 in a nuclear reactor. So you can imagine, because it goes from cobalt-59 to cobalt-60, it's going to gain a neutron.
Yeah.
And it gains a neutron through bombardment, which is essentially when I just put something and I speed up other particles to super high speed and they collide.
Okay.
Yeah. And the other one is technetium-99m, that isn't actually a typo. It is called 99M. And that is used in medicine for pinpointing brain tumors and is made from the radioactive decay of molybdenum-99, which is a byproduct itself in the nuclear fission of uranium-238.
Okay.
So it gets pretty complicated.
Yeah.
But you won't have to do it, which is pretty good.
Yeah.
So do you have any questions about that?
No. Yeah, I'm all good.
All right, no problem. And then the final thing this is the fun thing for the lesson, I guess, but we can continue, I guess. So we also have relative atomic mass. So what is the relative atomic mass? Well, the relative atomic mass is actually the mass that you see on your periodic table. So for oxygen, it's going to be 16. For helium, it's going to be 4. For hydrogen, it's going to be 1.08. For chlorine, it's going to be 35.5. But what does it mean by relative atomic mass? Well, the relative atomic mass is actually the average mass of all of the various isotopes in the element by the relative abundance. So what that means is essentially calculated in this equation where we have the percentage of isotope 1 times its mass plus the percentage of isotope 2 times its mass plus the third one plus the fourth one, so on and so forth, divided by 100.
Okay.
Yeah. So for example, I've done chlorine. So 25% of it is going to be chlorine 37 and 75% of it is going to be chlorine 35. So therefore, the relative atomic mass is actually 35.5, which is what it is on the periodic table.
All right. What's a mole?
A mole is from module 2, and it is the number of elements, the number of atoms it takes to, how do I put this? The number of individual atoms it takes to fill up, well, not fill up, the number of individual atoms it takes to get 12 grams of carbon-12.
All right.
Yeah.
Okay.
Yeah. So carbon is 12 on the periodic table. It's 12.01. And carbon, yeah. Okay. Yeah, 12.01, and then it's how many atoms it takes to fill up that. So it's pretty confusing, but you know how a dozen is the word associated for 1 mole? A dozen is the word associated for 12?
Yeah.
Yeah, a mole is the word associated with how many atoms it takes to get 12 grams of carbon-12.
Right. Okay.
And that number is 6.022 times 10 to the 23.
Okay.
Anything else?
No, that's it.
All right, no problem. So do you want to do the concept check for me?
Yeah.
All right, cool. How are you going?
I'm still on to question 1.
Oh, okay. Would you like some help?
No, it's just I need to fill the table in.
Okay.
Yeah.
No problem. I suggest referring to your periodic table for help.
Yeah, yeah. I'm done.
All right. Let's go through your answers.
Yeah. So for question 1, the number of protons for MO is 42,
Yep.
and then electrons is 42, and neutrons is 54.
Good job.
For copper, which is the second one, Cu,
Yes. Good job.
the mass number is 64.
Mm-hmm.
The number of protons is 29. Yeah. And then carbon, the atomic number is 6.
Mm-hmm.
The mass number is 14.
Yeah.
So the number of protons and electrons are 6.
Yep.
And the neutrons are 8.
Yep.
Is it phosphorus?
Yep.
Yeah. So P. The mass number is 31. The number of protons and electrons are 15. And the number of neutrons is 16. And then sodium, the atomic number is 11. The mass number is 23. Number of protons and electrons is 11. Yep.
Yeah. And that's essentially, that's just kind of get your understanding right about what A and Z, being the mass number and atomic number, actually are.
Yeah.
All right. What about question 2? So like, sorry. Before you start, index form was just referencing the double subscript,
Yeah.
superscript. Yeah.
Um,
So just tell me. So when you tell me the top number first, bottom number second, and then the symbol.
all right. So A, hydrogen 2 would be 2, 1 hydrogen.
Mm-hmm. Or it would just be 2, 1 H.
Oh, H. Yeah.
Yeah.
Then carbon 12, it will be 12, 6, C.
Yep.
For 3, A would be carbon 14,
Mm-hmm.
and B would be hydrogen 3.
Yep.
And for the it would be 69.1 times 65 in brackets plus 30.9 times 63 in brackets all over 100, which would give you 64.38.
Yeah, and if you actually were to look at your periodic table, so I'll get mine out. Copper is 63.55, so very close.
Yeah.
So you're right, but I just want to just for deeper thinking. So the answer you got was not, it was close, but not entirely accurate to the actual relative atomic mass of copper. So what do you think happened?
Well, since they're isotopes, they have a different mass, which mean to the oh wait,
Yeah, that doesn't really work because we account for the different masses by adding them up.
well, I guess it's not entirely accurate, which is why you don't get the same answer.
Yeah. Why don't you think it's entirely accurate?
Because it cannot simply be 65, whatever unit it is. It has to be. It's probably rounded.
Yeah. Also, another thing is that there may be more than two isotopes.
Okay.
So for the question has told you that there's only 2 isotopes of copper, but we've gotten the number that isn't actually equal to the real number. And this is because in nature, in the real world, there may exist more isotopes. So hence that will affect the relative atomic mass.
All right.
Does that make sense?
Yeah.
Okay. All right, so that's essentially it for today. This was a much shorter lesson. Would you like to continue with radiation, or do you want to like ask any questions? Do you want to go over anything? Do you want to go through the homework with me? Whatever you want.
Yeah, no, I'm fine with this. So, yeah, I'm okay with everything so far.
Okay. So what do you want to do?
Move on, I guess.
All right, no problem. So we'll begin a little bit of radiation, but this won't be in your homework. So we'll come back to it next week.
All right.
Yeah. So we kind of established what isotopes were. And we looked at radioisotopes were essentially isotopes that well, generally arrangements in the atom that result in the atom having to spit something out. And that is the radiation. So when we look at radiation, it's essentially a form of decay. So that's when the nucleus removes something because it has to get rid of something, otherwise the whole thing's going to fall apart.
Yeah.
So when an atom undergoes radioactive decay, it is basically breaking apart and releasing energy as particles or waves. So the reason why earlier it was atomic number 82 is because after this, everything undergoes radioactive decay because the nucleus is not stable anymore. And these elements are collectively called transuranium elements. And the vast majority of these transuranium elements are not actually found naturally in conditions here on Earth, and so are artificially synthesized, such as technetium-95 and promethium-146. Remember, the 95 and 146 correspond to the mass number.
Right.
Yeah. So the three main types of radiation that you'll be looking at is alpha, beta, and gamma radiation. So first we're going to do alpha. So I'm going to introduce something called decay equations. And decay equations are pretty important because they help us, what's happening? Because they help us actually find out what's happening in these equations. So initially, so alpha decay occurs when an atom emits an alpha particle. Alpha decay, alpha particle. And an alpha particle is made up of 2 protons and 2 neutrons joined together. And this is equivalent to a nucleum helios. Alpha decay usually occurs when a nucleus contains too much mass. So it removes 4 units of mass from the nucleus through spitting out a helium nucleus.
Right.
Yeah. So in alpha decay, an alpha particle is ejected out of the nucleus of the atom. So essentially the mass number just decreases by 4 and the atomic number decreases by 2. And there's an example here. So this is the most typical alpha decay equation that you'll come across. And so we have uranium-238 undergoes alpha decay to create thorium-234.
Right.
And what's actually happening is shown in that image. So we have the parent nucleus, which is the nucleus of the uranium-238, and then the decay happens, and we have an emitted alpha particle and the corresponding daughter nucleus.
Right. Okay.
Yeah. So I just want to draw your attention the equation. And for this equation, draw. For this equation, it's very important that we understand what's happening. So in this equation, when I explain it to you, it'll probably be obvious, but for now, there's two equations that are happening at the same time. We have the top equation and the bottom equation. The top equation is basically saying that is basically following the law of conservation of mass. Do you know what the law of conservation of mass is?
No.
Okay.
Conservation of energy.
Okay, so what's the law of conservation of energy?
Energy cannot be created or destroyed, but it can be transformed or transferred from one substance.
All right, good. So using that logic, what do you think the law of conservation of mass is going to be?
So I guess mass cannot be created or destroyed.
Yeah, so all it means is that the mass that we have before the reaction must be equal to the mass at the end of the reaction. And as we can see, we have 238 is equal to 234 plus 4.
Right.
So this equation is correct.
Okay.
And the second equation is, well, remember, it's the number of protons. So it's going to also follow the law of conservation of mass because we have 92 protons. So then we get 92 equals 90 plus 2. So that's how you write these equations. So for example, let me just pick a random one. Okay, I'll do the next one. So let's say thorium undergoes alpha decay. So 4,2He. What is going to be the other thing? What is going to be the daughter nucleus?
Does the element change?
Well, did the element change in the example?
Thorium and uranium are different, right?
Yes.
Yeah. They just broke apart.
Mm-hmm. What do you think?
So 80, the element with the atomic number of 88.
Yeah.
Which is
Just tell me the symbol.
radium, Ra.
Okay. And what is its mass going to be?
Its mass is going to be 230.
Yeah, which makes a lot of sense. So that means that when thorium undergoes alpha decay, it's going to produce radium 230.
Okay. Yeah.
So this is how different, well, this is exactly how radiation works. This is a form of radiation. But it's very important to note that it happens, this type of radiation occurs when we have too much mass. So we spit out 4 units of mass.
Yeah.
Does that make sense?
Yeah.
All right, cool. Do you have any questions about that?
No.
All right. So just to clarify, those equations will be used in all types of radiation, not just explicitly alpha.
Yeah.
But you are going to have to remember why each type of radiation occurs, because they each have their own specific reasons why they occur. So for alpha, it's because there's too much mass.
Yeah. Okay.
So if we go to the next page, we can see beta decay. And beta decay occurs when an atom emits a beta particle. And a beta particle is typically an electron. It can be a positron, but we're not really concerned about that at the moment.
Mm-hmm.
So in normal beta decay, so this is the reason why beta decay occurs, there are typically too many neutrons. And beta decay is usually the most trippiest one, is because when there's too many neutrons, one neutron will split into a proton and an electron, and it will send the electron out of the atom.
Okay.
So, yeah, so we'll see how that works in the equations.
Okay.
Yeah, so the key things to note is that since the neutron turns into a proton, the mass number is going to stay the same, but the atomic number is going to increase.
Right. Okay.
So therefore, beta decay causes an atom to change into another element with the same atomic mass. So that means that it turns into another isotope.
Okay.
Yeah. So we have the example with lithium-8. So I'll share my screen again. So for lithium-8, we can just very simply see an electron gets spat out, and everything's going to add up. So the top equation is going to be 8 equals 8 plus 0, and the second equation is going to be 3 equals 4 minus 1.
Yeah.
So everything has to add up because of the law of conservation of mass.
Right.
Let's just kind of do one together. What is going to be the beta decay of, what's a legitimate one? We'll do carbon-15. What does it decay to?
The beta particle.
Yep. So that's just an electron.
Yep. And okay. Nitrogen, so N. -15, yeah.
So it undergoes beta decay to produce nitrogen 15. But is nitrogen 15 an isotope, or is it the usual element?
It's close to the usual element.
I beg your pardon?
I mean, it's close to the mass of the element.
But is it the original element?
No.
Okay, so if it's not, what must it be? What is nitrogen 15?
An isotope.
Yeah, and will this isotope undergo further decay?
No.
It depends if the isotope is stable or not.
Oh, yeah, okay.
Yeah, because if the mass attractions are greater than the electrostatic force now, it's going to be normal.
Right, yeah, okay.
Yeah, so it's important to consider that.
Okay.
Okay. Okay, so the next thing is positron emission. So I know I said I won't really talk about it, but however, I did have a question on it in my prelim. So we'll talk about it just a little bit. So positron emission. So what is a positron? Well, a positron is basically a positive electron. It is the an electron.
Right.
Oh, oh, wrong one. Well, do you know what antiparticles are?
Well, it's basically like, it's not. Oh, I don't know how to pronounce, like, not pronounce it. To explain it, it's when it's not exactly that subatomic particle. It's that. Oh, it's basically a positron, but with different characteristics to a proton. Or
Yeah, it's kind of like that. So an antiparticle is the same mass but opposite charge.
okay,
So a positron is the antiparticle of an electron. So it's going to have the same mass of an electron, which is typically 0 in these cases, but it's going to have the opposite charge of an electron, which is going to be -1, +1.
right, okay,
So because of that, you can probably imagine what the equations are going to be like, but the reason why positron emission occurs is that it occurs in isotopes that have too many protons. So regular beta decay was for too many neutrons, positron emission is for too many protons.
okay.
Yeah, and let me ask you this. In proton decay, a proton splits into a neutron and a positron. Why does it split into a neutron and a positron?
Uh, oh, I'm not exactly sure.
Okay, look at the mass of a proton and a neutron and a positron.
So a positron has the same mass as a proton.
As an electron, 0.
No, yeah.
Yeah.
Electron.
Mhm.
And so a neutron. Neutrons have a heavier mass,
Neutrons weigh the same as protons.
weigh the same as protons.
Yeah.
Mm. Oh. I still don't know.
Okay, so let's look it through the lens of the law of conservation of mass, and I'll introduce a new rule, the law of conservation of charge, which is kind of the exact same, but it's just with charge. It's kind of what we've been dealing with in the previous examples, where the charges must add up, similar to the mass. So by the law of conservation of mass, initially with the proton we have a mass of 1, don't we?
Yeah.
And what is the mass of a neutron?
1.
And what is the mass of a positron?
0.
Yeah, so that works by the law of conservation of mass.
Yeah.
Similarly, by the law of conservation of charge, what is the charge of a proton? Just one proton by itself.
+1.
Yeah, what is the charge of a neutron?
0.
Yeah, and what is the charge of a positron?
-1. +1.
Okay, so that's why this works.
Right, okay. Yeah. Now I get it.
So that's exactly why the proton splits into a neutron and a positron, and why a neutron, so if you go back to beta decay, it said that a neutron splits into a proton and electron. Well, the masses are the same and the charges add up to 0, don't they?
Yeah.
So that's why that works for regular beta decay, and that's why this works for positron emission.
Right. Okay.
And then there's the associated equation. Do you want to go over that, or do you feel confident with those?
Yeah, I feel confident with them.
Okay, no problem. And the last one that we're going to be looking at is going to be gamma radiation. Also, one last thing I'd like to point out. So, you know, in the titles for alpha decay, beta decay, and gamma decay, those little letters in the brackets are the associated Greek letter.
Right. Okay.
Yeah, just for your knowledge.
Yeah.
So gamma radiation is the strongest form of electromagnetic radiation. So you remember on the electromagnetic scale, we had radio, microwave, blah, 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 all the way up to X-rays and gamma rays. So gamma rays are actually the most intensive electromagnetic radiation. And correspondingly, gamma radiation occurs when an atom emits gamma rays. But when does it emit gamma rays? Well, an atom will always emit gamma rays, usually after alpha or beta decay. And this is because the nucleus is still excited. So all it means is that there's excess energy.
Okay.
So because there's excess energy, because it just booted out a helium nucleus or an electron or a positron, it has to release energy in the form of these gamma rays in order for the nucleus to stay stable.
Right.
Yeah. But what is the equation? Well, there actually isn't an equation because gamma isn't actually a particle.
It's energy, basically.
Yeah. So if you were ever asked to write an equation, all you would do is write, I don't know, let's do 10, 5a, and that's going to go to 10, 5, they're just placeholders. Plus 0, 0, gamma.
Okay.
Because it doesn't have a mass and it doesn't have a charge.
Right. All right.
Yeah. So it's just a release of energy following regular decay because the atom has to get rid of energy, otherwise something's going to happen.
Okay. Yeah.
Yeah. And there's a very interesting consequence of this, and it's the fact that gamma radiation, it's actually not a type of decay because only energy is released. No mass is being released, is it?
No.
So it's not a form of decay.
But it's still radiation.
Yes, it is still a form of radiation. It's just not a form of radioactive decay.
Right. Okay. Yeah, I understand.
Yeah. And that's essentially it.
Okay.
Yeah, so I hope today was pretty insightful in learning a couple of things. You did join the Google Classroom, which was good. I saw you join, so everything's all good. You do not have to attempt the properties and structure of matter homework 1 because I presume you already completed that because that was last week's homework.
Yeah.
But from now on, please go on to there for the new homework. So homework 2 is posted. It's going to be due next week before our lesson. I will, if you don't send it to me like the night before or something like that, I should have it ready for you next lesson.
All right. Okay.
Any questions?
No, I'm good.
All right. Thank you.
All right. Thank you. Bye.
Bye-bye.